Hi, this is Dr. S.P. Harsa from Mechanical and Industrial Engineering Department, IIT Roorkee. I am going to deliver my lecture 18 on the subject of the strength of materials, and this course is basically developed under the National Program on Technological Enhanced Learning. As you see, in the previous lecture, we have discussed about that if we have a cylinder, then and in the cylinder if we have the steam or any kind of pressure is exerted on the walls of the cylinder along any direction, that means you see along longitudinal or radial or the circumferential direction, then what the stress components are there, which stress components were dominating in that, like you see as we discussed that the two main stress components are there, they are always dominating in the longitudinal as well as the hoop, or we can say the circumferential part. So, generally see whatever the stress components which are inducing due to the application of this internal pressure are always considering in two mutually perpendicular direction. One is along the length, that is the longitudinal stress component, that is the sigma L, and another one which is along the circumference, that stress component is known as this circumference or the hoop stress. So, that was you see we discussed, and also we found that if you compare the equilibrium portions of under the application of this pressure, then this longitudinal stress component is nothing but equals to PD by 4T, or this hoop stress or circumference stress component will be it is PD by 4T. So, this we discussed, and then we found that if we are going for to measuring just to measure the deformation, that actually how the deformation is there along the longitudinal as well as the circumferential direction, then we found that we have the longitudinal strain component and we have the hoop strain component, and if you want to compute the longitudinal strain component, then it is nothing but equals to sigma L by E, because this is the longitudinal one. So, sigma L by E minus the Poisson ratio into sigma H by E. So, you see if we compute both the thing in terms of the dimensional parameter, then we have a longitudinal strain component which is nothing but equals to PD by 4 TE into 1 minus 2 times of Poisson ratio. So, that you see we computed, and similarly you see we applied the same theory along the circumference of or circumferential portion of the thin cylinder, and we found that we have a circumferential or the hoop strain component, that is the epsilon 2. Also we computed that it is nothing but equals to sigma H by E minus mu times of sigma L by E, where sigma H and sigma L are hoop stress as well as the longitudinal stress component. And if we compute these two terms on the basis of their dimensional parameter, then we found that the epsilon 2, which is a circumferential or hoop strain component is nothing but equals to PD by 4 TE divided by 4 TE into 2 minus mu. That means you see the Poisson ratio. So, we computed both the component, that what exactly the corresponding change is there or corresponding deformation is there in terms of the strain component, and then you see and accordingly we computed that what the change of length is there, that the epsilon 1, that is the longitudinal strain into original length, and if you want to compute the change in diameter is nothing but equals to epsilon 2 into the original diameter, and epsilon 2 is nothing but the circumferential strain. So, corresponding you see we can simply calculate that what the deformation is there or what the change is there in terms of length as well as in terms of diameter. And then we discussed about the volumetric strain, that you see we are finding that the change in length is there, change in diameter is there, then definitely you see if we are considering in the volumetric domain, then we have a volumetric strain, and we found that the volumetric strain is computed on the basis of longitudinal strain and hoop strain, and there is an exact relationship which we set up in the previous lecture, that this volumetric strain is nothing but equals to this longitudinal strain plus 2 times of hoop strain. And if you put those things, like we have the longitudinal strain is PD by 4 TE into this 1 minus 2 mu, and hoop strain, that is PD by 4 T into 2 minus mu. If you put both together, then we have a volumetric strain which is nothing but equals to PD by 4 TE into 5 minus 4 times of mu. That means you see we have both all three components are there as well as the strain things are concerned. That means you see that what exactly the deformation is going on in terms of length, in terms of diameter, or in terms of volume, we can simply compute. So, that part we discussed when we have a thin cylinder with no specified shape at the end. But you see if we put the specified shape, that means you see if we have a spherical corners and like both spherical corners are having different thickness as compared to the wall thickness of the cylinder. That means you see if you are considering that wall thickness is T1, and if then definitely you see we have a spherical wall thickness at the extreme corner is T2. But if you are keeping the diameter is same, then we found that definitely we have like the hoop stress component in the cylindrical portion is different than the this hoop stress component in the spherical part, and corresponding changes are there. That means this hoop or circumferential strain in both of the portion, means cylindrical as well as the spherical portion, were different. So you see we computed both the thing, that if we have a cylindrical portion, then the hoop strain is nothing but equals to PD by 4 T1. If T1 is the thickness of the wall of cylinder, then T1 times E into 2 minus mu was there. And if we are computing this hoop strain, or we can say the circumferential strain along you see like the spherical portion, then we found that it is nothing but equals to PD by 4 T2, and T2 is the thickness of the spherical cell into E multiplied by 1 minus mu, that means the Poisson ratio. So you see here we found that there are like significant differences there in cylindrical portion as well as the spherical portion. And then you see now like if you want to compute the common portion, that what exactly the relation is there to avoid the distortion at the junction portion. That means you see like because there is a spherical portion at the end, and there was you see like the cylindrical portion is there, so obviously there is a very good chance to have a bending as well as the shearing stresses at the junction point. So to avoid those things, we set up like we discussed that actually there is a ratio of T2 by T1, and in that you see if the wall thickness of a cylinder is 2.4 times wall thickness of the spherical portion, then you see we have a continuous structure from cylindrical to spherical portion, and you can simply avoid the distortion at the junction point. So these kind of relations which set up, but all those discussion in the previous part like was set up when there is no shearing portion, only these two mutually perpendicular normal stresses were there. So now you see we just want, because like this cylinder, when there is a rotation, means if we have like the shaft is there and if it is rotating, and then you see like the kind of internal pressure or the kind of different pressures are exerting, then what will happen. So now you see in this lecture we are going to discuss that actually if we have a sphere or if we have like the rotating shaft is there, then what the kind of stresses are being dominating and how we can set up the relationship in between the stress component. This kind of like the discussion is going to be there in the next lecture. So here you see in this lecture 18 we have the first portion, that is the thin rotating ring or cylinder. And considering a thin rotating ring or cylinder, which like I'm going to show you in the next slide, is just subjected to a radial internal pressure P. That means you see now we have internal pressure towards the radial direction of this thin ring, or we can say the thin cylinder, caused by the this centrifugal effect, because you see now this is rotating, so definitely we have a centrifugal center through which the centrifugal forces are exerting on like this radial direction of this rotating ring, or we can say the this cylinder, and that due to the centrifugal effect of its own mass, when it is rotating, always we have a kind of centrifugal stresses. So the centrifugal effect on the unit length of a circumference, because it is always acting in the circumferential part of this particular rotating ring. So we have now P, which is like the internal pressure is always acting towards that, is equals to mass, is nothing but the mass of this cylinder into omega square, that at what point it is rotating, because now you see we have a rotational speed, so m omega square into the radius, where you see the radial pressure P is acting per unit length. So here you see like we are saying that at per unit length how this P pressure is exerting on the wall of this cylinder. So this you see like P is always as the this force per unit length. So you see corresponding the change is there, and it is caused by the centrifugal effect, because it is rotating if its own mass is you see like having a rotation, and this rotation is there at the omega, that is the rotational speed is there. So corresponding, like we can simply calculate that what will be the pressure is there, and pressure is m omega square r. So now you see, by considering this particular figure, as I told you that we have like this thin cylinder or the rotating ring. So this is rotating, and as I told you, we have a centrifugal center. So from this center now, since it is rotating at omega, so obviously you see whatever the forces are coming, that will be coming as m omega square into r will be given, there is a pressure, and thus you see the considering the equilibrium portion, because you see what we have a same symmetric section is there. So we are simply cutting the portion. So you see this is the half portion which we are cutting, and in the half portion we can simply see that this is the radius of the thin cylinder, and since you see like the internal pressure is exerting all along the circumference of this particular specified shape of the cylinder, we will find that these are the internal pressure which are always going towards the outer circumferences, because you see we have a centrifugal action which is always dominating in this kind of rotating devices. So due to that we have this kind of like the pressure exerting on those things, and we have the force which is you see like perfectly there on these particular cutting sections. So you can see that we have a different forces which are dominating at different sections, and we need to be very careful that actually when these forces are acting on the different portions of this body, what is the effective area under which these forces are acting. So this you see, by considering the equilibrium portion of the half of the ring which is showing here in this figure, we can simply say that the force which is you see at these two extreme corners, you can simply see these two extreme corners. So both you see, by considering both portion, 2 times of F is nothing but equals to P times of 2 times of R. Again you see here we are assuming that we have like the unit length, that means whatever the pressure which is exerting is always pressure per unit length, and 2R is the projected area, because you see this R is there, and like the total R, that is the diameter, because this pressure is exerting all along this diameter. So this P into 2R is the effective portion of this cylinder is there. So it will give you 2 times of force which is exerting on the cylinder. So we have force which is exerting pressure is nothing but equals to P times of R. So you see here like we have considering that whatever the rotation is there of the cylinder is constant, that means it is constantly rotating at omega, and omega is nothing but equals to the rotational speed of this shaft, or we can say the cylinder. So corresponding forces are always dominating, one due to the internal pressure. So you see circumferential pressures are there, and one is along that you see the force. So this F is there. So we can say that one P is omega square R, this is one part. Second you see we have the F which is nothing but equals to P times of R. So you see, by considering the F as in like the diametrical portion, so what we have, since it is you see the diametrical part is there along these like this perpendicular direction or the y direction, we have the hoop tension, or we can say the hoop compressions are there along with that. So F is the hoop tension set up according to the rotation, and the cylinder wall which is like assumed to be so thin that the centrifugal effect can be assumed constant all across the wall thickness. So here you see what we are considering. We are considering the first thing, that whatever the wall like thickness is there, it is like the pressure which is exerting on the circumference of wall is always uniform, and it is like uniform in terms of pressure per unit length. And second assumption which we assume, that the cylinder wall is so thin that whatever the centrifugal effect is there on those wall, it is having a constant all across the wall thickness. That means whatever the centrifugal forces are coming, they are uniformly acting. So whatever the deformation is there, they are also like uniform. That means there is no stress concentrations are there, or there is no distortions are there which are different at different regions. So as you see, we discussed that the hoop tensions are there at the diametrical portion. So this is nothing but equals to mass into acceleration, and you see here if you are considering the acceleration, that is omega square r into r, and if you like multiply with the mass, so we have you see m into a, that is the applied force. So m omega square r into r, or we can say m omega square r square is there, and since this is like as a tensile force, due to that you see always there is a chance of extension is there towards the circumferential direction, or we can say the hoop stresses which are inducing due to this particular rotation under the application of this internal pressure, always we have like the tensile hoop forces are there, and this tension is transmitted through the complete circumference, because we are assuming that the circumferential effect is uniform all across the wall thickness. So obviously you see whatever the transmission is there, this tensile forces transmission, this is also you see like the uniformly distributed. So this tension which is transmitted through the complete circumference is always uniform, and therefore is resisted by the complete cross sectional area, because like it is not that actually, as I told you, that there is no stress concentrations are there which are different at different regions. So they have the uniform way. So whatever the cross sectional area is coming under the action of these tensile forces, it has to be uniform and it has to be considerable equally. So hoop stresses, as I told you, the force, the hoop tension divided by area. So you see the force which we computed previously is mass into acceleration. So mass m into omega square r square divided by area, because this area is the effective area under the impact of the circumferential like the effect plus whatever the forces are applying due to P. So now this unit length, assume m by a, because we are assuming that the pressure is applied per unit length. So this unit length assumption is always coming into the picture, and m by a is nothing but equals to mass of the material per unit volume. That is, you see now like with those kind of the density, we can say that the hoop stresses are nothing but equals to r into omega square r square, or we can say sigma h is nothing but equals to this density into omega square into the r square. So we can say that since the mass, we are considering that this mass of material per unit volume, always density will come. So you see here like what we are doing here, we are simply considering with the density rho into omega square r square. So this is our hoop stresses. So with the consideration of the hoop stresses, always we are assuming that these hoop stresses are along the diametrical portion and it is in the tension. So whatever the deformation is coming, these are the tensile, like means we can say the percentage elongation is positive. So these are always in the positive directions. So now you see like with those kind of conditions, we can say that the hoop stresses are there, and these hoop stresses are due to the circumferential part, due to the this centrifugal portion along the circumferential part, and this is nothing but equals to this density of the material rho into omega square r square. So this is the hoop stresses. Now you see here, if you are saying that these members, these thin cylinder members which are subjected to the torsional load, that means you see if a kind of shearing is there. Till now you see whatever we discussed, we only discussed about the normal stress component, that you see we have a normal stress component, they are acting along these two directions. So you see along the longitudinal or along the hoop stresses, and that is what you see we were simply discussing. Even if it is rotating, only the hoop stresses are dominating, and you see these are coming due to this density into omega square r square. But you see if there is a shearing portion, that means if you see a kind of couple or moment is acting on a particular the particular area or particular direction, then what will happen, then what kind of stresses are there. So this you see like here we need to concern the torsional effect on a circular shaft. So you see the definition of torsion is pretty simple, that considering a shaft which is shown here, that we have a particular shaft which is rigidly claimed on a one end. That means you see we have a shaft which is, you can say, a kind of cantilever part. One end is rigid and one end is free. So we can simply apply the kind of load, couple, moment at the free end, but one end is absolutely rigid, so we cannot apply any kind of action on the fixed part. So if we consider the kind of shaft which is having a cantilever feeling and which is claimed at one end and twisted at the other end by the torque, and always you see when we are applying a torque, always there is a force at the extreme corner into the diameter. So you see this torque is F into D, which is applied in a plane perpendicular to the axis of a bar, such that the shaft is said to be torsion. That means you see what the forces is always applied in such a way that they will just try to tend this like this shaft in a some direction. So if I am saying that actually if they tend to move this shaft in a clockwise or anti-clockwise direction, always there is a distortion is there, and this distortion is not along the axis, this distortion is there along a plane. So if I am saying that you see this is my plane, and if I apply a torque is there, the kind of distortion is there along this line. So here you see in this shaft, if I am saying that these forces which are applying along these things, so they will just try to tend this shaft into a anti-clockwise direction. So whatever the distortion, because and this will tend to resist this kind kind of motion like that. So now we have a shearing action here. So one end is opposing and one end is in action, and what will happen then? We have a torque which is F times of d. This is the diameter of this particular shaft. So what will happen, this the kind of, you see, this rotation or the twisting will come into the shaft, and the twisting, the direction, you can see this particular slide that the twisting will be there along this direction. That means, you see, like this direction will be affected more as compared to this x axis. So we can simply compute the kind of deformation, and this deformation is computed by phi. So phi is nothing but the distortion in the shaft, and this shaft is under the we can say rotating part, or the couple is there. So whatever the shearing action will come, this will computed as a torsional. So torsion part is there. So now what the effects are there of the torsion? The effect of the torsional load which is applying on a bar is to impart an angular displacement of one end cross section with respect to the other. That means, you see, like as I told you in the previous, we have a phi. So how phi is coming? Because of the distortion, and this distortion is since along the circumference of the shaft. So this phi is always known as the angular displacement, not the uniaxial. It is an angular displacement, and angular displacement is always coming for a particular plane direction. So that's what you see, we have a shearing part. So to set up the shear stress on any cross sectional bar is always perpendicular to its axis. That means it is not the axial part, it is always perpendicular to one axis. So now you see these two major impacts are there on the kind of rotating shaft wherever you see the couple is applied on that. So now you see, we just want to see that how these shearing stresses are occurring on those things. So we have the physical understanding of the phenomena of particular this setup of the shearing stresses in a shaft subjected to a torsion can be easily understanding by taking a different applications, that how these forces are being applied and how this cross sectional area is to be affected under the application of this like the torsion or the couple or any kind of, you see, the moment is there at some of the corners. So now you see here, now we are taking the three different cases, and we would like to analyze that actually how these stresses are being set up in those things. So first, you see, now what we have a cylindrical member, or we can say a shaft which is in the static equilibrium, and this particular torque, you can see this part, these torques are simply applied, okay, in a resultant external torque, which is just like is a member, because whatever the members are there of this particular shaft, they are acting in such a way that they are just try to act and react in a particular direction, and let the member be imagined to be cut at some section on a plane M cross N. That means, you see, what will happen now, just look at this particular figure. We have a simple shaft, and at these two corners we are simply trying to apply the torque. So the corresponding torque, how it will come? It will come, you see, like in this side, if you are talking about the right side of this particular portion, it will just try to tend this shaft in a clockwise direction. Then you see, we need to apply, like in opposite way, or we can say, like this kind of force, so that we can say that this under the application of this torque, now our shaft is in equilibrium position. So what will happen, you see, if we are considering that if we have a one segment, this MN segment, only we just want to see that how these the shafts, the torsional portion is to be acted. That means how these like the torsional stresses are being set up within this shaft. And since I told you that it is a circumferential portion, so always it is like acting all across this particular circumference of this rotating shaft, and this is always going as a diagonal part, not along the axis, as I told you in the previous section that it will be perpendicular to the this axis. So you see here, now this is the great impact. So the torque is like trying to rotate in this clockwise direction, as I told you, and you see now we have the another portion. If we just want to make this segment as an equilibrium, then we need to apply in an anti-clockwise direction. So you see, this is the one significant effect is there. Middle portion is also affected by the real cause of rotation. So you see, we have like this circumferential part is there, which is, and the layers of this circumference of this particular cylinder will always tend to move in this direction. So you see here, there is no elongation towards x direction or y direction, only they are simply tending in the circumference of those things, okay. So On the other end, you see what we are doing here, we are just trying to put the this opposite torque is there. So, there is a net effect is there on this kind of thing. That means, you see, like the first thing which we discussed, that actually if we cut the portion in the middle one, then you see, like we found that actually this middle one is in a equilibrium position only under the application of those things. But if we the figures the previous figure which I shown you, when a plane is MN, means if we cut that particular portion and if we see that the portion on right hand side, what we get that actually like the entire member is subjected by the applied force and the remaining force are just trying to settle down the layers of this thin shaft. That means, you see, like whatever the distortion is there, and if we want to like restore those portions, we need to apply the equal and like the opposite direction of this kind of torsions just to make the layers in a perfect way. So, since the entire member is in equilibrium position, as I told you, that is what therefore, and each portion must be in equilibrium. That means, whatever the layers or the distortion of the layers are there, they have to be there in their original position by under the application of these action and reactive torsions. Thus, a member is in equilibrium under the action of resultant torque T and developed like the resisting torque TR. So, always you see like you will find that they are just trying to tend in a real manner, so that whatever the torque which are applying, they can simply form in a resultant torque TR in such a way that it can simply oppose, and they will tend to like this portion in an equilibrium way. So, now you see here this one more figure, this is a third case which we can simply see that now these the portions are just like that. When you are simply applying the load, the kind of distortion, as I told you, like, so these are the rotational part. If I am saying that these are the small segments are there, so these all small segments are just trying to tend in the particular direction, or we can say these are the layers. If you are considering, then they are layers are just tending to move in this direction under the application of this load. So, what will happen? We will have a distortion. So, if I am considering those distortion or the phi which I told in the very first figure, that we have a angular displacement is there. So, if I am considering the angular displacement, and if it is the radius of r is there, then this this tau into dA will give you that what exactly the distortion is. That means, how distortion like distortion is taking place in a shaft under the application of this torque. And then you see like and all those, even not only since we are cutting this section along the x axis, so this distortion is there, but if you see all along these like the entire portion, you will find that the layers of the entire portion is equally affected under this particular application of these torques. So, you see we need to consider these things. The previous figure which I shown you, it simply shows that how the resultant torque is simply like developing, because if until unless if resulting torque is not like applied, then probably you see this permanent distortion will take place, and then you see there is a the failure will start along the diagonal portion. So, you see equal and these resisting forces are always dominating wherever you see the couples are there along any axis. So, the resisting torque TR is simply produced by a virtue of infinitesimal, that means the small portion of shear stresses acting on a plane perpendicular to the axis of shaft. And that is what I told you, like like wherever these torques are applied, these like the layers are deforming in a perfect way, because the shearing action is there on individual segment of the layer. So, and if we are just combining those segments, we will find that there is a complete distortion is there all along from the resisting portion to the extreme corner, and then these are, you see, at this rigid corner always it is very small, but as you go along where the point of application of this torque is, you will find the more of distortion is there, because the layers are so set up in such a way that that shear stresses can be easily acted on that, and the resultant torque can easily equally applied in a resisting way. So, obviously such shear forces would be developed by virtue of these shearing actions, or we can say the shear stresses. So, we can say that actually whenever when a particular member, or let us say we can say a shaft is subjected to a torque, the result would be like that on any of the element there will be a shearing action is there which is acting. So, whatever the layers are there, as we found that actually we found that the shearing action or shearing action is there on these individual elements, and they are tending to move in a opposite direction. But if we are saying that the object is in equilibrium position, always we have a equal and opposite part, and the technical term for the equal and opposite shearing stress is the complementary shearing stresses or complementary shear forces. So, if I am saying that any object which is you see on like under the rotation and there is a couple is acting, the shearing is there, all elements which are like under the influence of this couple, they are simply experiences the shear forces and they will just tend to move along the circumference part, not along the axis, just towards the plane part, and then you see we have equal and opposite portion which is coming to balance or to equilibrium that portion, and these shearing forces are known as the complementary shearing forces, always comes into the picture whenever the action of this nature is there. Thus we can say that when a member is subjected to a torque, an element of this member will subjected to a state of pure shear. Always keep this thing in mind. If we are saying that this member is there and the torque is applying on that member, any the shaft, beam or any rotational portion, if we are saying that torque is applied, couple is applied on any of the power portion, it is simply applied like because under the application of this torque, these whatever the portions are there or the elements are there or the microstructures are there, or we can say the layers of these portions are always under the action of pure shear. So shearing is coming in that way. So if you are saying that the shafts are like the machine element and which we are using for transmitting power, and if due to the action of this torque like they are like coming with those kind of forces, whatever the stresses are inducing due to the action of the couple or the torque on this kind of shafts, rotating shaft, they will be under the action of pure shear. But now you see we have the different like kinds of moments are also there. Means we cannot say that only the torque will give you the kind of feeling of the shearing stresses, but if we have a twisting moment, what is the meaning of twisting moment? The twisting moment for any section along a bar or shaft can be easily defined that the algebraic sum of the moments applied like just couple which we are applying the couples that lie on one side of the section under consideration. That means you see like if we are saying that this is a rigid bar like just like the cantilever bar as I shown you in the previous figure like, and you see the couple is acting. Okay, so these kind of twisting moments are there, they will just try to twist them like either the bar or shaft, and you see like the kind of distortion will start it from the action starts like that. So if you are saying that one section which is under the kind of these moments, and if you are summing those applied couples or the moments, we are saying that the choice of that side in any case is always you see like the arbitrary is there, but in any case what we have a kind of distortion in all those kinds of segments, and if we sum up those segments we will find that where the applied forces are there we are more distortion, where the rigid sections are there we have a small distortion, and due to the impact of these moments. So we can simply sum up those twisting moments as such, and due to that the kind of distortion is always coming into the picture, and they will be in the form of this circumferential part. That means you see the circumference is always tend to move in a particular direction. So if you want to compute the distortion as such, we are saying that, or the deformation, always a strain form is coming, and since we are saying that whenever twisting moment or couple or any kind of like the torque is applied on the kind of the shaft, or we can say the bar, always what we have, it is under the state of pure shear. So if we are saying that due to the pure shear this deformation is there, and which we are measuring in terms of the strain, the kind of strain is always known as the shearing strain. So you can see this particular figure that if like we have a simple shaft is there, and since it is simply unloaded, that means there is no load application is there, there is no torque is there, then it will simply show the layer of these shafts are just along the AB. So now this is AB is there, which is pretty simple. So if a generator AB is marked on a surface of an unloaded bar, you see there is no distortion is there, there is no load application, the layers of these bars are well like stabilized manner, and they are perfectly like a stabilized way. So now if we apply the torque, so here you see the torque application is there, or the twisting moments are there on both of the corners of this particular shaft, then what will happen? Then after a twisting moment T has been applied on this particular like line, and this line will move, the resultant of the twisting moment, tend to, this B portion will shift it to B dash. That means, as I told you, the layers are so deformed or distorted that these portion, the like these are nothing but this is the layer and this is the deformed layer. So undeformed layer to deformed layer, we are gaining some sort of distortion, and the angle this gamma, which is also known as the strain, shearing strain component, is simply measured in radians between the final and the original position of the generator. And always you see, since we are saying that it is measuring all along the circumferential part, or all along we are saying that towards the plane. So this distortion which is measuring in terms of angles or in terms of the radians, these strains are known as the shearing strains, and always they are acting not along the axis, along the plane, or we can say along the circumferential part. And the same definition will be holding for any kind of interior portion of the bar. That means you see like as I told you that like there is an individual impacts are there on the individual component of these bars, and they are always tend to move. That, as I told you like clearly, that like these all these internal portion or along this particular length, they just try to like move along the circumferential part due to the application of this twisting moment. So as a resultant, if I am saying that like now this is the stabilized manner, so we will find that there is a distortion, and this distortion is, as we are computing in terms of shearing strain, so this you see the angle will clearly gives you the kind of distortion, and this angle is known as the shearing strain angle, or we can say that this B dash will be is nothing but equals to the shearing strain. So this is a real significance of shearing strain. So whenever a shaft or a bar is under the application of twisting moment or torque, we have a state of pure stress which are acting on these particular bars, and due to that we have a distortion which can be easily computed in form of the strain, and these strains are known as the shearing strain, and these strains are always acting along like the plane, or we can say along the circumferential part, which can be easily computed as we can simply like shown in this particular figure. So now you see like what we are doing here, we are simply saying that we have a stress, we have a strain. So obviously, since we are considering the stress and strain, since both stress and strains are the shearing part, and we are assuming that these under the application of these like the twisting moment or the torque, these deformation or the stress formation is under the elastic one. So we can simply apply the Hooke's law, and for which always we are defining the Young's modulus of elasticity, and since here the shearing moment is there, so Young's modulus will not be applied, because Young's modulus is only applicable wherever the normal stress components are there. So here we are applying the shear modulus of rigidity, because it is shearing action is there. So as we discussed, you see in the previous chapters that we have a G, which is the Young's modulus of rigidity. So the modulus of elasticity in the shear, the ratio of shear stress to shear strain will give you the modulus of elasticity, or you can say the rigidity in the shear, or modulus of rigidity, means both have the same meaning. Doesn't mean, since here it is like the distortion is there along the plane, so we are saying that the modulus of rigidity, otherwise you see it compute the same kind of like the relation that the shear stress divided by the shear strain will give you the shear modulus of rigidity G, and it is always denoted by the G. G is a capital capital Z is there, and in that you see like if you are saying that we are measuring the angle of twist. So how we can measure, as I told you in the previous section, that since there is a shearing action, and with the shearing action there is always the distortion is there. So this distortion is more at the this extreme corner where this twisting moment is applied. So this you see now, this is the angle which gives you a clear feeling of the shearing strain. So if a shaft, if I am saying that the shaft is of length L, which is subjected to a constant twisting moment T. So these are the T you see along its length, then angle theta will always gives like that actually how much distortion is there, and through this like always one end of bar will twist relative to the other end, and this angle is known as the angle of twist, because wherever the shearing action is there, always the angle of twist is forming, and if we can measure the angle of twist, it will give you that how much distortion is there, and this distortion is it gives you a clear feeling about the shearing strain. So despite the differences in form of the loading, whatever you see in terms of the twisting moment or couple or whatever, we see that there are number of similarities there in between the bending and the torsion, including for like a linear variation of the stresses and the strain within that particular effective position. So, in torsion you see the members are subjected to the moments in a plane normal to always towards the means these axons. That means you see we are not considering wherever the torsional axis these torsional axons are there, we are not considering that what's going on with the axial form, only we are considering that what is the impact is there perpendicular to these axes, or we can say along the plane. So, this is one you see the clear which gives you a clear feeling about the bending as well as the torsional part. For the purpose of designing a circular shaft to withstand the given torque, because you see like whatever the torque is there, due to that always there is a kind of shearing forms are there. We must develop an equation which will give the relationship between the twisting moment, maximum shear stresses produced due to the action of twisting moment, and a quantity which represent the size and shape of a cross sectional area of a shaft. So, you see here what are the influencing parameter just to design just to design a shaft or a bar. First, the main thing is that actually what exactly the twisting moment is applying due to that. So, you see once you know the magnitude of, or once you know the nature of the twisting moment, corresponding shear stresses are there, because you see once we can say that okay, now the twisting moment is applying at the extreme corner or the middle portion, or due to this reason like that the couples are there, immediately you see the shear stress, the impact is there on the shear stresses. So, what is the maximum shear stress which is producing due to the application of the twisting moment, and then you see like the corresponding quantities there which represent, means this is the clear dimensional parameters there, because if we have a bigger shaft or a smaller shaft, if we have a thin shaft or the thick shaft, then you see definitely, or we have a hollow shaft or a rigid shaft, what exactly the shape and size is there, this will also like influence the design of this particular kind of shaft. So, you see we need to consider these kind of parameters if we want to design the shaft. So, not all you see the torsal problems like involves the rotating machine, in which particular like this rotating machinery. However, some of the examples are there like the suspension systems which employ the torsional, like you see the torsional springs, they are always under the action of the shearing part. That means you see like if you see this particular figure, you will find that all these coils are there of the springs, they are like as a curved surfaces are there, and they are under the action of the torsion. So, you see whenever we apply the load, always they have the kind of like the twisting is there all along, that you can see this particular figure that they are under like the twisting moment. So, whenever we just want to design those things, always we have to consider that actually how these moments are taking place and what is the effective area under which these moments are there. Once you set up the twisting moment, then the immediate action, as I told you, will come, that actually what will be the shearing action is there under the action of this twisting moment. Once you know those things, the twisting moment as well as the shear stress, then the next is there that how many number of coils are there, the n number of coils, and what is the effective diameter of these coils. You see, you can see these things. So, these are the key features, and if you want to design those things always in terms of the spring, because spring is nothing but they are simply based on the stiffness. So, what you see like the force per unit deformation is there under the action of these shearing part. So, we need to consider the stiffness, that how much stiff of this the stiffness is there in the spring, that means how stiff these spring parts are there, how many number of coils are there. This is very important figure, and then you see what the twisting moment and the shearing stresses are occurring in those kind of the springs. Many torque carrying engineering members are always you see the cylindrical in shape. So, that is what you see like we need to derive that whether it is like shaft is there, bolts are there, screwdrivers are there. So, how we can like see that actually the twisting moments are playing on those, especially these shafts or the bolts, or we can say kind of the springs, and how the maximum shear stresses are coming into the picture. So, you see here in this particular chapter what we discussed, we simply discussed that if a member is under the action of pure shear, that means you see if I am saying that if a member is rotating, then how the like we can say that the pure shear will come into the picture. And if we are saying that like all the elements which are there within this particular cylinder, they are under the action of the pure shear, then what will happen? Then you see the complementary shearing component will come to stabilize like this particular member in a equilibrium manner. So, once we have this kind of phenomena, then immediately it comes that actually if you let us say if we have any kind of circular bar which is under the action of the couple, then what will happen? If we want to design those kinds of things, then actually we have to be very careful that actually what is the affected area or which these rotating planes are there, and then if we are saying that these shearing actions are there, then what is the shear strains are there, okay? Because when we are saying that this is under the action of couple or twisting moment or torque, then shearing is there straightway, it is under the action of pure shear, and because of the pure shear we have the shearing strain. Once you have the shearing strain or this kind of thing, then you need to measure that actually what exactly the shearing strains are there, or how the distortion is taking place under the action of pure torsion. And once you stabilize those things, you see we have a angle theta which is known as the this angle of twist, and corresponding you see like since we have the shear stress component, we have the shearing strain component, obviously we have this new constant, that is the since it is the under elastic deformation. So, we have the new constant which are measuring the relationship between, or we can say which are setting the relationship between the stress and strain, that is the shearing modulus of rigidity. So, you see shearing modulus of rigidity G is nothing but equals to shear stress tau divided by epsilon, or we can say gamma, that is the shear strain. So, we can measure all this kind of things, and you see it is applicable equally this twisting concept to the springs also, because springs are always, you see wherever some twisting is there, these all coils are simply subjected by the twisting moment or the torque, and corresponding like if you want to design those things, how these stresses are being set up within that structure, we have to be careful. So, in this chapter you see we discuss those things. Now, in the next chapter our main focus is that actually once we have like the rotational shaft, then how we can compute those things. Still only we set up that these stresses are there, these strains are there, but how we can compute those part if we have a moment at the middle portion or at extreme corner, or if we have a simply supported beam, or if we have a cantilever. So, what will happen, and what the real impact is there of the shear stresses. So, this kind of discussion which we are going to discuss in our next lecture. Thank you.